so your homework assignment for Wednesday is to finish your analysis of the graphs. We have done the derivatives, hopefully you've got them all right now for almost problems on page 215. And I'm going to give you several examples to show you what you need to do to finish the analysis and complete a decent sketch of the graphs. So I have a few examples for you. Here's the first one. And again, I'm going to assume that you've already got the first derivative and the second derivative. I'm not going to go over how you get those. So the first thing that you always do when you are looking at analyzing a graph is you ask yourself if there's a domain issue. And this first problem is a polynomial, so the domain is all real numbers. And that's what makes it a little bit easier, so we don't have any domain issues. And then the next thing that we're going to do is take a look at our first derivative, and I'm going to look at where the first derivative is equal to 0. I've got this in nice factored form, so I can see that already. X is equal to 0, and x is equal to 2. And always consider where the derivative is undefined, and again, this is a polynomial, so that it's not going to happen here. I'm going to go ahead and do an interval test to look at what's going on with this graph. And, a little too high. So my critical numbers are 0 and 2, and I just plug it back in, do my interval test, positive, negative, and positive. So I know that this graph is going to go up, and then go down, and then go up again. I'm going to do the same thing for my second derivative, looking for possible points of inflection. And I have a possible point of inflection x equals 1, and the second derivative is undefined, doesn't happen anywhere. I'm going to make an interval test for this. Notice that I'm labeling my interval test so that people know what I'm doing, and plug in the numbers on either side of 1, and I get negative and positive. That means the graph is going to be concave down and then concave up. So for each one of the problems that you have, you want to get this set up, and we have done this several times, so just be really careful about it, make sure your derivatives are right, and be careful when you're plugging things in. Now, the next thing you want to do is lock down any points that you know are on the graph. So, for example, we know that we have critical numbers at 0 something and at 2 something, so I want to go ahead and figure out what are those two values. And you just do that by taking it back and plugging it back into the original equation. So this will be 0, 3, and 2, negative 1. Be careful when you plug those things back in, because getting these points wrong makes the puzzle pieces not fit together correctly. I'm going to go ahead and do this for my point of inflection also. These points need to get locked down, and then you're just really playing connect the dots and making sure that everything works together. So there are the 3 points I have to do. My job is now to draw a graph that contains these 3 points and meets the conditions of increasing, decreasing, then increasing, and also meets the condition of concave down followed by concave up. You do not need to put it on graph paper. If you feel like you need to put it on graph paper, think again. Try to do this just by sketching it, getting an idea of things. Lock your points down and label them. Notice that that's a flat point, so you might put a little mark there indicating that when you go through that point, it needs to be sort of flat. And then 2, negative 1, somewhere around in here, also flat. And then 1, 1, somewhere around in here, not flat. That's where my concavity changes. Now you need to connect these 3 points so that the conditions that are shown in those interval tests are met. So the concave down and then concave up, increase, decrease, increase again. I think this one's a pretty straightforward one. And there we have a nice little polynomial function. Now, one other piece of information that you sometimes want to include on the graph are the zeros. And my general rule is to include them if they are easy or if they're required. If you actually are asked for them, of course you want to include them. So I'm going to go back and look at that original problem up here. And that doesn't look particularly easy. That's a cubic. So I'm just not going to bother doing those this time. Okay? So that's a pretty easy one. Let's try another one here. I've already done the derivatives. So we're just going to jump right in and try to go through all the steps. The first thing is that you've got to make sure you pay attention to the domain. This time we know that x cannot equal 0. And take a minute to decide what's happening there. You knew how to do that from your pre-calc class. So we know that that's a vertical asymptote at x equals 0, right on the y-axis. Okay? And We also want to notice that there is a horizontal asymptote, limit at infinity. This is a rational function. Our coefficients here are 1 and 1. And so, I mean, our exponents are the same in the numerator and the denominator. And so our limit at infinity is going to be 1. We're going to have horizontal asymptote at y equals 1. So when you start to draw your sketch in a few minutes, you want to get those two asymptotes on there before you do anything else. Okay? And I'm going to set up my derivative information. F prime equals 0, and that's nowhere. F prime undefined, and that's going to be at x equals 0 because there's a vertical asymptote there. Second derivative, F double prime equals 0, nowhere. Double prime undefined, again at x equals 0. I'm going to do my nice interval test here. And I like to just remind myself that the derivative is undefined here. It's not flat. People are making a mistake when I draw the graph. It is still a place where the graph can change from increasing to decreasing. Now, in this case, since the denominator is x squared, it's always positive, and the numerator is -2. So this graph is always decreasing, except at 0 where it's undefined. And the second derivative changes. To the left of 0 is concave down, and to the right of 0 is concave up. Okay. Now I don't have any points that I can lock down on this graph. I didn't find any points because these x values that I got here are my vertical asymptotes. But I do have some asymptotes to draw in. This is kind of tricky to draw in. You know, I kind of leave it around a little bit like that so I can see it. And then my horizontal asymptote here. Make sure you label it as 1. I need. You remember what graphs look like when you have these asymptotes. It's either going to be up above in this area up in here, or it's going to be down in this area. Either one of those or the other. It's not going to be in both places. So you just need to figure out which one it is. This graph is decreasing and it is concave down. So it looks like this. It's decreasing and it's concave down. It has that shape to it. And you just need to see whether that goes up here. Well, that's not what asymptotic behavior looks like, so that's not going to be it. Or down here. And there it is. You might want to go back and see if that 0 is easy to find. I'll look at that in just a minute. Okay. And then on the second half of the graph, it is decreasing and concave up. So it's going to look like that. Decreasing and concave up. And again, that doesn't make any sense for it to be down here in this area. That's not what asymptotic behavior looks like. Okay, it's going to start here and decrease to right here. Okay, and that's what our graph looks like. Now, in this case, that 0 is pretty easy to find. Back up to the original problem, and you can see where does f of x equals 0 from right there. It's going to be at x equals -2. So since it's easy to find, you might as well go ahead and put it on there. Okay, and that's our sketch for the second example. All right, let's take a look at the third one. This is one of those where the derivative would have been a little bit more complicated. All right, and but we're just going to work through it just like it is here. Notice that we have a domain issue. The domain is that x cannot equal 2. There's vertical asymptote at x equals 2. And there's one other issue with this one. There's a slant asymptote for this one. I'm going to get the derivative information on here first, get that all worked out, and then I'm going to talk about the slant asymptote for this problem and how I knew there was one and how we find it. I know you did it last year, but you may just maybe have forgotten it here. So first let's get the derivative information. So first derivative equals 0 at x equals 0 and at x equals 4. Now one of the things you might want to do is right here, just go ahead and find your 2 points. Get that out of the way right at the beginning. Remember you plug that back up into the original problem. Turns out to be 0, -2. And 4, 6. All right, f double prime equals 0 is nowhere, and f double prime undefined is at x equals 2. Oops, I forgot that over here. F prime undefined at x equals 2. Because we've got that vertical asymptote, so that's going to show us all of them. Okay, I'm going to do my interval test. So f prime, you have to include that 2 on your interval test. because that's a place where things can possibly change. So it's going to be at 0, 2, and then at 4. And we're going to test those, and it is increasing, plugging it back into the first derivative. The denominator is always positive, so I can just check the numerator. And then decreasing, and then on the other side of 2, it is decreasing and then increasing. And again, I'm just plugging those numbers back up right in here into the first derivative and checking for their sign. All right? My second derivative, the only thing I have to check around is 2, and plug those numbers back up into your second derivative, and it looks like on the left side of 2, it is concave down, and on the right side, it is concave up. So we've got all this information about our derivatives. This is all stuff that we have done before. Just have to be careful with it. And now we need to remember how to do a slant asymptote. Okay, if you're going to get a slant asymptote, if the degree of the numerator is 1 more than the degree of the denominator, if the degree of the numerator is 1 more than the degree of the denominator, you're going to have a slant linear asymptote. Okay, so this problem, I'm going to write the problem over again. We have x squared in the numerator, and we have x in the denominator. So it's exactly 1 higher, the power of 1 more than 1 in the denominator. So there's going to be a slant asymptote. So to find the slant asymptote, you do long division, or if you remember how to do it, synthetic division. I'm going to do long division this time. And I will just work it out. Hopefully you have not completely forgotten it, or it'll come back to you. And both of these go away, and I end up with just 4 here. So when we wrote this back in Algebra 2, you would have done something like this. You would have said that f of x is equal to x plus 4 over x minus 2. The function here and the function here are the same thing. They're just written 2 different ways. You put it in your calculator and looked at the graph, they would be exactly the same graph. Okay? This right here, this piece right here, without the remainder, if you ignore the remainder, this gives you your slant asymptote. Sometimes these are called oblique asymptotes. I'm not sure which one your textbook last year told you. So we have a slant asymptote of y equals x, okay? And you just leave that part off of it. You leave this, does not come into the slant asymptote. All right, now we're going to put the whole thing together. We've got lots of information. X and Y axis. We have a vertical asymptote at 2. We have a slant asymptote at y equals x. And I think you remember probably what these graphs looked like from your work last year. You're either going to have this or you're going to have this. It's going to be one of those 2 things and not both of them. And so, get rid of those, so find out which one it is. Okay? You then need to put together all the other information that you have from calculus to figure out which one it is. And the second half of it is either going to be up here or down here. It's not going to be both. It'll be one or the other. Okay? We've got a couple of points that we need to graph. It was 0, -2 right here. And that was a little flat place. And go right back up here. All the stuff. Both of these 2 things right here were flat. And this one is undefined. It helps you to write that in. And go ahead and write those pieces of information in. And at 4, 6, it's also going to be flat. So that's going to be over in here, flat. And that should be enough to tell you what's going on, just because you've seen these graphs before. But still, we know that the graph increases, decreases. So that's increases, flat, decreases. Okay? And then on the other side, it decreases and then increases. Decreases and then increases. And you can double check the concavity. It was concave down, and then it is concave up. Okay? All right, and you should definitely label those points as well. Do that. I don't see any other zeros that I need to label, and so that problem is finished. All right. Okay, what I'm going to do now, this last one we're not going to work all the way out. I'm just going to remind you of how to do the slant asymptote again. Make sure you know how to do it. I'm not going to actually work this one all the way through. So it has a slant asymptote because the degree of the numerator is 1 higher than the degree of the denominator. So again, I'm going to do this by long division. If you remember synthetic division, you're welcome to do synthetic division. You can Google it. It doesn't work for everything, but when it works, it's pretty fast. So, okay, this time I'm I'll subtract away. When I do this subtraction right here, -4 minus -3 is -1x. I'm going to bring that 4 down. So I'm going to get -1 here. And it's -1x plus 1. And my remainder is 3. The remainder doesn't really make any difference. This part right here is your slant asymptote. So for this graph right here, you have a vertical asymptote at x equals 1 in the denominator. And you have slant asymptote at y equals 3x minus 1. And then you would put those two things together with all of the other derivative information if I asked you to graph this. Okay? One other one. Number 5. I'm just going to do one more with the slant asymptote. This one you would not be able to do synthetic division. If you go look it up, synthetic division doesn't work if you have an x squared or an x cubed here. It only works if you have just today. So when you get ready to do long division on this one, again, the degree of the numerator is 1 more than the degree of the denominator, so there's a slant asymptote. So when you get ready to do your long division here, you want to put in some placeholders for the placeholder for the missing x squared. There's no x squared term, so you want to put in an x squared term down here of 0. It just helps keep things lined up. Sometimes you can manage without that, but often makes it easier to keep things all lined up. Okay, so I'm going to do the division here. This will give me 2x, and that gives me 2x to the 4th. And when I multiply 2x times 8, that's going to give me -16x. So you just want to keep things lined up, put things in places that make sense. Okay. Right, and then you're going to subtract, and that's going to give me 6x plus 8. And the thing is, at this point, I'm done because I can't put x cubed into, sorry, mistake, I'm not done. I need to bring out -5x cubed, the 0x squared, 6x, and I'm going to go ahead and bring down 8 as well. All right, and then I'm going to have a -5 here, and that's going to give me 5x cubed and 40 over here. I'll line things up so that they make sense. And you can bring anything down that's left over, 6x minus 32. And now I'm done because I can't take x cubed and put it into 6x. And here is your slant asymptote. So for this problem right here, we have a vertical asymptote where x cubed minus 8 equals 0. That's going to be at x equals 2. And you're going to have a slant asymptote at y equals 2x minus 5. Okay? All right, so hopefully that'll get you through whichever problems have slant asymptotes on them. All right, so now I'm going to give you just a list of things that you need to keep in mind when you are working through the analysis and the graphing of these problems. First of all, make sure you take a look at the map, okay? In particular, list any vertical asymptotes or any other domain issues that you might have. Second, you want to do horizontal asymptotes and slant asymptotes. I don't have both. They cannot have a horizontal asymptote and a slant asymptote. And if you'll think about how rational functions look and how you figure out horizontal asymptotes and slant asymptotes, you'll see why. You're going to need to take your derivative, which you already have, and you're going to look at your critical numbers. Okay, and then you're going to do some work to figure out whether it's increasing or decreasing. Right? So you take a look at your second derivative, and your possible points of inflection. So you're going to look at what its concatenating is. And for these, we're going to do interval tests. Make sure that they're labeled. Okay. Then you're going to make sure you find points. At this point, you're going to have some x values. Okay, so make sure you get your x, y. And when you do those points, you might note to yourself whether they are flat or whether it's a point of inflection or exactly what's going on at that point. And then this is optional sometimes. Find the zeros. It's easy. It just sometimes makes the graph a little bit easier to put together. Okay? Alright, so those are all the things, and then you got to put it all together so that everything matches. If it doesn't match, then you have made a mistake somewhere. One other little comment about domain. One of the domain issues would be if you have a function that's the square root of some stuff up underneath there, then when you want, when you're dealing with the domain of that, you would take the stuff that's under the radical, it's called the radical, and make it greater than or equal to 0. And if that is linear, you may solve it just by easy algebra 1 methods, but if it's not linear, then you want to take the radicand and set it equal to 0 and interval test to determine where it is positive or negative. Okay? Alright, and then one other thing that didn't come up in the examples is if you get f prime of x is undefined, but f of x exists. In other words, there was no vertical asymptote there. Remember that that gives you two possibilities. What you're looking at is either a sharp turn, so it's going to be your points here, it's not going to be flat, it's going to be a sharp turn like this, or it might go like this, like this. So some sort of a sharp turn, or it could be a vertical tangent line. So if it's here, it might go up, get vertical just for an instant, and then come back around like this, or it might come down, come back around like this. And the way that you tell the difference is by looking at all of the other information, your f prime information and your f double prime information. So for example, all of these pictures here, there is the slope is undefined at that big point that I've marked. Here it is increasing and then decreasing, and it's concave up on both sides. Here it is increasing and decreasing, but it's concave up and then it is concave down. Here it is decreasing and then increasing, and it's concave down on both sides. This one here, it is increasing and then it increases again, and the concavity changes. It's concave up followed by concave down. So each one of these is slightly different, and you have to put all of the pieces together. Okay, the homework is for you to do problems on page 215, those odd ones that you had done the derivatives for, and to get all of this done for each one of those problems. In addition, you'll look at Friday's homework on page 215. There are 6 problems. They're all even. You might want to go ahead and take those derivatives for those problems, problem 8, 10, 14, 16, 20, and 24. Just maybe get the first derivatives taken. If we're out for a second day, I will post those derivatives, and then you can go ahead and get started on those afterwards. All right. Good luck, ladies.